This is a short video showing how you can use PV equals nRT along with a situation wherein you have some mixture of gases. So for my little cartoon, we'll have a balloon that's been filled with some oxygen gas generated above some water. So this will be my water here. And I'll have some of the water vapors in black here that have filled up a container. We'll say that we've generated a total of 1.02 liters of gas above this water of, again, this will be our oxygen gas. And the temperature that we have of this gas is 293 Kelvin. And the total pressure of this gas is 755.2 millimeters of mercury. So what we're going to do is try to find, using not just PV equals nRT, but a relationship of partial pressure. So we'll say the pressure of oxygen is equal to the N amount, that is the N is the mole amount of oxygen in this gas, over NT, that's the total moles, black plus orange, times total pressure. So we're going to connect these two relationships. First we're going to find the total N, that's in here, we'll put that here, and then we'll be able to solve for our amount of oxygen in moles, and we'll be done with this problem. So let's find the total N. We'll take the pressure and have to convert that to atmospheres using 760 millimeters of mercury to divide this by. So that would give us, if we do a division of 755.2 by 760, we'll get 0.9937 atmospheres. So we just converted that millimeters of mercury to atmosphere so that we can use PVnRT, or pressure constant R times T, R being equal to 0.08206 liter atmospheres over mole Kelvin. Remember, we need to use these units within the other variables. So let's put this together. We have our pressure now as 0.9937. I'm just going to write in the numbers and not put in the units, as long as I have the same units that are in my R value, times the volume, 1.02. And we're isolating N. We want to find N, so we're going to divide this by R and T. And temperature, we said, is 293 Kelvin. Again, making sure that we're using the same units that we have within the units for our constant R. Now if we do that math, we get 0.04216 moles of gas. That is blue, the orange and the black. That is our total moles of all these gases. So we have our NT value. We now have NT, and we already have the pressure total, the 0.9937 atmospheres. And what we need to do to find our last needed variable, partial pressure, is we're going to have to take what is a table that is giving us a certain amount of water vapor that's known to be in the gas at a certain temperature. We're going to take that from a table, and we're going to say that the pressure of water over that surface is 17.55 millimeters of mercury. This is the pressure of water at 20 degrees Celsius, which is 293 Kelvin. So if you take that and subtract it from 755.2 and then divide by 760, we'll know the pressure of our oxygen. So I've gone ahead and done that. We know if we work that out again by taking the millimeters of mercury total pressure, subtracting the partial pressure of water, we can know the pressure due to these gas molecules that are orange. That's the O2, and we'll divide that by 760. If you do that, you'll get a value of, for the pressure of oxygen, of 0.9707 atmospheres. Alright, so now we're ready. We can put this in, put the PT in atmospheres in, we have NT, and we can solve for O. So I'm just going to show that equation and we'll be done. So we put this in, 0.9707 atmospheres. We set that equal to what we're looking for, or N, number of moles of oxygen. Total N, we had just calculated as 0.04216, and we times that by our total pressure we had as 0.9937. Now I'm leaving the units out, but we can then isolate our N, number of moles of oxygen, and then we'll be done. That's it.